The flap. 350 millimeters of brake drum at the front, 275 at the back. And it still was not enough, so Mercedes bolted a door to the car. This is the Mercedes-Benz 300 SLR. It won Mercedes the World Sports Car Championship that season, and it went to Le Mans on drum brakes while the Jaguar beside it had discs. A drum holds its heat inside a closed pot. Work it all afternoon and the pedal goes long. Their drums were so big they would not fit inside a 16-inch wheel, so all four came off the wheels entirely onto short half shafts bolted to the chassis. Alfred Neubauer's answer was not more friction. It was air. A hinged panel nearly the width of the car, lying flat behind the driver's head, hauled upright by hydraulic rams on a dash lever. At the end of the straight, he pulled it and the car walked into a wall of air. There was a linkage meant to drop it again when second gear went in, though some drivers had that taken off and worked the lever themselves. So why is there not one on your car? The disc brake made it pointless. A disc hangs its friction surface in the open and sheds heat as fast as it makes it. It does not fade. Once you can brake as hard and as often as you like, there's no reason to carry a wardrobe door on your back. The fix was never more air. It was better friction. The inside out. This looks like a drum brake. It is a disc brake. It is a disc brake built inside out, and it was standard on the Chrysler Crown Imperial from 1949. The Ausco-Lambert. Instead of a caliper squeezing a disc from outside, two discs sit inside a cast iron drum and are forced apart outward onto the drum's inner faces. The drum is the part bolted to your wheel, and it is the part that spins. The discs barely turn at all. It is a drum brakes layout with discs doing the rubbing and the friction pointing the wrong way. Between the backs of those two discs sit steel balls, resting in conical divots. The pedal makes the first contact. After that, the drag takes over. The two rings twist against each other. The balls roll up the ramps and shove the discs apart, harder. The car's own rotation finishes pressing your brake on for you. That is self-energizing, and a feather-light pedal produces an enormous clamp. It came from the Auto Specialties Manufacturing Company of St. Joseph, Michigan on patents by an engineer called Homer T. Lambert. Lighter pedal than a caliper disc. Less fade. Cooler running. More friction area than the drum it replaced. So why did it die? Nobody bought it. Outside the Crown Imperial, it was an option costing around $400 on cars selling for a few thousand. Chrysler put the best brakes in America on the order form, and almost nobody ticked the box. It was not beaten in a test. It was beaten at the dealership. Brilliant is not the same as worth it. The button. There's no brake pedal in this car. There is a rubber mushroom on the floor. It moves almost not at all, and it is the brake. The Citroen DS 1955. Everything on it ran off one pump, and the brake was the strangest thing that pump did. Underneath ran one central hydraulic circuit at about 2,500 pounds per square inch, driven off the engine. That one circuit did the suspension, the steering, the brakes, the clutch, and on the full DS, the gear change. The brakes tapped pressure that was already sitting there, which changes what the pedal is for. An ordinary pedal is a lever. You push it a long way to generate force. The button generates nothing. It meters what the pump already made, so it does not need to travel. Press harder and you get more braking. Press a little harder and you get a lot more. And that is exactly how it died. Not badly built. Badly matched to the human being. Every driver alive had learned braking as a distance, and the DS asked them to learn it as a pressure. The first experience of a DS was stamping on it and nearly putting your face through the windscreen. Citroen kept it for 20 years across the DS and the SM. Nobody else copied it, and when the CX came along, they kept the hydraulics and the pressure, and gave it a pedal shaped like everyone else's. The engineering was right. The drivers were not. The Freeloader? This is a brake booster with no vacuum, no pump, and no electricity in it anywhere. It steals from the driveline instead. The Rolls-Royce mechanical servo. Invented by Mark Burkitt in 1919 for the Hispano-Suiza, licensed by Rolls-Royce almost immediately, and fitted from 1924. It is a disc clutch wearing a different hat. A friction disc assembly lives in a bell-shaped casting off the back of the gearbox, splined to the universal joint, so it spins whenever the prop shafts touch the pedal, and you nip that spinning disc. The driveline grabs it, drags on the linkage, and pulls your brakes on for you. You supply the intention. The car's own momentum supplies the muscle. Rolls-Royce improved on the original too. Birkick's version only worked going forwards. Theirs worked both ways. The rod-operated version ran until the war stopped car production in 1939. But the servo itself never left. It went on boosting hydraulic brakes instead of rods, and the last Phantom fitted with one was delivered in 1978. 54 years. Here's the flaw. The servo does not care how fast you're going. It cares that the shaft is turning. Friction does not know about speed, so the help holds almost all the way down, and then simply stops being there at the one moment you're still asking for more. And if the driveline lets go, your assistance goes with it. A vacuum booster does not care whether the wheels turn at all. Borrow your muscle from the driveline and share its luck. The rust trap. The first disc brakes on an American production car were not on a Cadillac. They were on the cheapest car in the country. May 1949. Crosley made disc brakes standard on every car it built, 5 months before Chrysler turned up with its own completely different kind. They were designed by Jesse Hawley of the Hawley Brake Corporation and, despite what the adverts implied, they were not repurposed aeroplane parts. Hawley drew them for cars, and it was the right idea. A spot caliper pinches a small exposed disc from both sides. No drum to trap heat, no shoes to expand, and almost no weight, which on a car this light matters more than on anything else. On paper, Crosley leapfrogged Detroit by a decade. Then it met an American winter. The alloy calipers sat out in the open. The theory was that a spinning disc would fling the water off. Salt is not water. The alloy corroded. The calipers seized solid, and a brake that locks itself on is not an inconvenience. It is the car deciding to stop without asking. So in the middle of 1950, Crosley threw them away and fitted plain 9-inch Bendix drums. Nobody made them do it. Better shielding would probably have saved the whole idea. But Crosley Motors had just lost $1 million in a year and was not spending another cent finding out. The best brake is the one that works in March. The spinning brain. Anti-lock brakes in 1966, with no computer and nothing you could call a sensor. A spinning weight, a cam, and a switch. The Dunlop Maxaret, fitted to the Jensen FF, the first production car in the world with anti-lock brakes and the first road car that was not a mud plugger to drive all four wheels 14 years before the Audi Quattro made that idea famous. The trick is momentum. A small flywheel spins with the transmission at a speed that tracks the road wheels. Brake hard and the shaft slows fast, but the flywheel keeps going, because that is what momentum does. Two parts that were turning together are now at different speeds, and that difference is a physical signal that a wheel is about to lock. The disagreement works a cam. The cam closes a switch and the pressure drops for an instant and comes back as grip returns. The thinking is done by a lump of spinning metal. It came from aeroplanes where locking a wheel on touchdown is genuinely serious, and it was the first anti-lock system used widely anywhere. So why is there not one on your car? Because it won and then lost on the detail. Every car you can buy has anti-lock brakes. What died was this way of doing it. There was one Maxaret on the whole car driven off the center differential, so it read the average of all four wheels and released all four together. It could do nothing about the one wheel actually skidding. A sensor at every corner watches each wheel on its own, and against that there was no argument left. The idea outlived the machine completely. The Untouchable. This brake never touches anything. No pads, no shoes, no disc, no drum, no contact at all between the moving parts. The Telma eddy current retarder, French, still built at the same factory outside Paris. And unlike almost everything in this video, it is still fitted today. Coils sit around the driveshaft, energized in alternating polarities, making a magnetic field. Two rotors spin through it, and the field induces electric currents inside the rotor metal itself. Those currents make their own magnetism which fights the rotation. The rotor is dragged by a field it created by moving. Your momentum turns straight into heat thrown off through fins. Nothing wears out, because nothing rubs. 4 stages, so the driver dials in as much drag as the hill needs. It does not care what the engine is doing. Gearbox in neutral, engine stopped, it still brakes. So why is it not on your car? 2 reasons, and the second is fatal. It is heavy, a lump of iron and copper hung on the drive shaft. Precisely the wrong thing to add to a car. And it makes no force at all at 0 speed. It pulls hard nearly the whole way down the hill. Then in the last few miles an hour, the current dies with the motion that made it, and the braking falls off a cliff. It cannot stop you, and it cannot hold you. It is a retarder, and every vehicle carrying one still needs ordinary brakes as well. On a bus, worth it. On a car, not. The third pedal. 3 pedals in Mika Häkkinen's Formula 1 car, and not one of them is a clutch. The extra one brakes a single rear wheel. The McLaren MP4 12, and the idea is credited to Steve Nichols, the man largely responsible for the car that won 15 of 16 races in 1988. The rear brake line was split in 2. One half ran through an extra master cylinder plumbed to one rear wheel. Brake normally and pressure passes straight through it, and both rear wheels brake together. But press the extra pedal while accelerating out of a corner and it adds braking to that one wheel. Slow one rear wheel and the car rotates around it. You have steered with the brakes, killed the understeer, and stopped that wheel spinning up all at once. On the 97 car, it was plumbed to whichever side the circuit needed and stayed there all weekend. A year later, a switch let the driver choose corner by corner. Nobody outside McLaren knew. Then the photographer Darren Heath noticed a rear disc glowing red hot where the car should have been at full throttle. He later shot blind into Häkkinen's empty cockpit, and that photograph is the only reason we are talking about this. And that is what killed it. Not a failure, a rule book. Ferrari campaigned hard. The FIA decided it was a steering system rather than a braking one, and the stewards declared it illegal at the second race of 1998. It did not brake. It was legislated out of existence. The missing ones: take the wheel off this car and there is no brake behind it. The brakes are in the middle of the car, bolted to the differential. Inboard brakes. The Jaguar E-Type ran them at the rear from 1961. Lotus used them. And if you have been paying attention, you already met 4 of them at the start of this video. The reason is unsprung mass. That is the weight the springs are not holding up. Wheel, tire, hub, and brake. Every kilogram is weight the spring has to push back down after a bump while the damper fights to settle it. And the longer that takes, the longer the tire is not properly on the road. Move the brake inboard and the corner gets lighter over bad surfaces. That was Mercedes' second reason. The first was simpler. Their drums would not fit inside the wheel, so all 4 came off the hubs, the rears beside the differential and the fronts bolted to the chassis. So why did they go away? Heat and access. A brake at the wheel sits in clean moving air. A brake buried against the differential has almost nothing flowing over it, so it cooks, and a brake that cannot dump heat fades. Changing pads means going underneath rather than pulling off a wheel. Jaguar moved them back outboard for the XJ40 in 1986, 25 years after the E-Type put them there. Even racing gave them up in the end, for the same reason. The physics was right. Nothing else was. Subscribe if you like machines that were solved by something simpler, and next time we will find 9 more that nobody misses. Send it to the Scrapyard.